Very glad that Daniel invited me to give a mini lecture here about instruction tuning. This is a really hot topic recently. We started working on this topic probably 2 years ago with a bunch of collaborators, including Daniel. Hopefully, this talk will be beneficial to you, and I'm also looking for collaborations. If you want, we can talk offline. So let's start. Probably everyone has known ChatGPT and GPT-4 are really amazing. They can do a lot of tasks, and we call these models generalists because it's a really general purpose model. Basically, you can ask them to explain things, get brainstorming ideas, and ask it to write code. In the GPT-4 paper, they reported that these models help pass a bunch of exams. These are all challenging exams for college students or even professionals. In my case, I actually tried using these models to write a website. This website is a Flask, like Python Flask website. It has front end and back end. This is for my research. Actually, this is for evaluating these models. These are amazing, right? But the question is, how did these models acquire such a large amount of capabilities? There can be two sources. One is the pre-training. These models are pre-trained on a very large corpus from the internet, like the internet scale. In the GPT-3 paper, they reported the GPT-3 model has seen around 500 billion tokens. Another source of these capabilities can be the fine-tuning stage. After the pre-training, to get GPT-3 or like the initial GPT-4, OpenAI also fine-tune these models on some human labeled data. It's possible that this fine-tuning stage can also give the model some knowledge. But comparing the size of data in these two stages, the fine-tuning stage, as reported in the Yizhong GPT paper, only has 44K examples. In terms of tokens, this is 10,000 times smaller than the pre-training stage. I think we can draw a safe conclusion here that a lot of the knowledge and skills that the model knows came from the pre-training stage. However, this talk is focusing on the fine-tuning stage. I will try to convince you that this stage is actually very interesting and worth exploring. You can tune the model to any forms, and also it will become more and more important in the future. So the outline of this talk is based on two of my papers. Actually, Daniel was also the core author of these two papers. The first one is the supernatural instruction paper. I will talk about how we collect a benchmark for cross-task generalization. And this cross-task generalization is the fundamental of these general purpose model. In the second part, I will discuss our work, self-instruct, on replicating ChatGPT. Basically, we generate a lot of instruction data with the GPT model itself and try to improve the model with this generated data. Third part, I will discuss some of the recent trends and some future direction that I find promising. Let's start from some history stuff. The NLP research before 2018, if anyone of you has been working on this for a while, you know that we have a lot of benchmark, we have a lot of tasks like sentiment analysis, question answering, machine translation. These are usually different subfields that have different people working on. And actually we have we still have these different tracks now in the NLP conference like ACL or EMLP. So back then, people build models for each individual task. And they usually show, when they talk about generalization, they usually refer to instance level generalization, which means you have a training set in this task and you have a test set in this task. and your model after training on the training data can generalize to the testing instances. So I call this instance level generalization. And then starting from 2019, I think there is a very hot trend like on doing multitask learning. Basically, the purpose is still to get better performance on these training tasks, but they combine all these different training tasks, and they saw, okay, these tasks can benefit each other. One example is the DACA LLP. This paper is actually rejected by CLEAR 2019, but it's a very famous, and I like this paper. However, the problem with classical multitask learning is your model is still generalizing within the training tasks, not across tasks. So this is to say, if you have a like totally unseen task, there is no way that the model can do this task, because it's only trained to do the training task. It doesn't have any information of the unseen task. The only way to do cross-task generalization is to provide some information about the new task, the unseen task. This concept was explored in the Natural Instruction version 1 paper. Basically, they collected 60 tasks and annotated this definition, and they show, okay, with this definition, the model can actually generalize to this unseen task to some extent, not very much. But this concept is very cool, right? Like supposing you have a model, and now with this definition, like you can basically define new task to it, and it can do it, right? Like this is very promising. So in the supernatural instruction paper, we basically scale up this idea. We collect 1,600 tasks in 76 broad categories. These categories include the top one are translations, question answering, programming, question generation, and we have some like tasks across different levels. The sentiment classification is usually like sentence level or paragraph level. Word semantics is word level. We have dialogue format. We have this grammar error detection. It's a detection task. And overlap extraction. It's a very simple task, but it's a very simple, very core capability for the model. With those, with the large collection of the existing NLP tasks, we also annotate instructions for each task. By instructions, we actually have different fields, multiple fields. One is the definition. In our case, definition is a very, very informative and declarative format. It should be like sufficient to define the task to average human readers. This is our goal for annotating this definition. Look at one example, like for this squad QA, people might be familiar with. Our definition is like the task is about a reading comprehension task based on, and we define what is reading comprehension based on the information provided in the given passage. You should identify the text span from the passage. So this basically define how can you do this task. And we also have some information about what should be avoided, like avoid answers that are incorrect or provide incomplete justification for the question. Basically, this is a relatively informative definition of the task. And for each task, actually in the instruction field, we have positive example and negative example. These examples comes from the idea of in-context learning. Basically, you can also use these examples to teach the model how to complete the task, like what we do for crowdsourcing, for example. And then for each task, we have these instances. The model needs to read the instruction, understand the instruction, and follow the instruction to complete these instances, given given the input of these instances, and the model need to generate the output. To benchmark the cross-task generalization, we split the all the tasks into into the train and the test splits. The training split contains 700 tasks. This is because like some of the tasks were discarded because we have to make the train test split strictly overlapped. And in the test case, we have around 120 tasks covering 12 categories. So you can see here the testing category, like textual entailment, cause effect classification, coreference, like totally unseen during training time. Like these are not a generalization across data set, but it's a generalization across like real task category. So this is very challenging. And then, okay, I forgot to mention one thing. We train a model on this training set, and we call it a TK instruct. Basically, it's a T5 based model. I will not cover the details here, but the model is what we built. And then let's look at the performance. We first provide two very simple baselines to just use the shortcuts of these data sets, and it has relatively bad performance. And then we evaluate like vanilla pre-trained language models. T5 language model get only 30, and GP3 get very big jump here, but it's still like 45. And then we evaluate instruction tuned models. One is T0 from Hugging Face, and the other one is InstructGPT 001 from OpenAI. If you compare these two models, T0 versus T5, and InstructGPT versus GPT-3, you can see actually these models, like after instruction tuning, becomes better than the vanilla pre-trained model. But still, like the model we built, TK Instruct, outperform all these instruction tuned models. Basically, TK Instruct is based on the same T5 model as T0, but why the performance is much better? This is because the TK Instruct model has seen the training instructions of our data set. This data set is very large, and also the instruction style is kind of similar as our testing task. Although it's like cross-task generalization, the instruction style is still very important here. And then we compare with supervised training. This supervised training is a multitask trained model, like a multitask model trained on the testing set. So basically, this is can be regarded as the upper bound of this benchmark. You can see, okay, we are not very far from this supervised training, but there is still some gap. Actually, I know some work recently got 65 or 66 on our benchmark. So yeah, we are really making some progress, closing the gap between this cross-task generalization model and the supervised training model.
For the supervised training, you said it was trained on the test data. So how do you, I guess, like, how do you not just get 100% if you're training on the test data? Like, can't you easily choose
get
100?
Yeah, the model is trained on the testing task, but it's still not on the testing instances. Like it's instance level generalization.
Gotcha.
Like we have train and test splits for each task. Okay, so let's do some deep dive here to analyze what are the most important factors for this cross-task generalization. The most important lesson we learn from this like large collection of tasks is that the model, if you want to do the cross-task generalization, the model benefit a lot of from the diverse tasks. The left figure is basically the model's performance against a different number of training tasks. you can see consistent improvement here. But I should note that the x-axis is log scale. So as the training task grows larger and larger, the model's improvement starts to slow down. But still, like this curve hasn't stopped. So with more tasks, we expect the performance to continuously grow. The red curve is actually more interesting because in the existing NLP literature, when we propose a new task, we spent a lot of efforts annotating a large number of instances for each task. Here we analyze the model's performance, generalization performance against the number of instances per training task. We can see the model's performance peaked at around 100. Actually, this number is at 100 training task. So we can see here that as the number of training instances is smaller than 100, we see improvement. However, after you go over 100, the model's performance actually starts downgrading. This is because in this cross-task generalization, actually overfitting is a big problem. Because our goal is not to learn the training task, but to learn how to follow instructions in doing new tasks. So we should be very careful about this kind of overfitting. Including using more training instances actually won't help. Then another big factor we found very helpful is the model size. We basically experimented with different sizes of T5 model, and we see very consistent improvement and actually very big improvement after we use the largest model. However, I want to mention that even with the larger model, if you train on like a small number of tasks, you still see big drop in terms of performance. So both model sizes and data sizes are very important in this stage. We then analyzed the different elements in our instruction field, which contains our task definition, the positive example and negative example, all these combinations. We found that actually the most effective combination is the definition plus positive example. This is basically to say, okay, both the instruction following and the in-context learning with examples are helpful for the model to generalize to new tasks. So we just use this as the default setup. Okay, takeaways for this paper. We really demonstrate that this cross-task generalization via instructions is plausible. And we provide this data set called SuperNI instruction. Actually, I still think this is a very good playground for instruction following. It's a very small, so if you want to train model, it usually take hours. Like all the other data set, they use a large number of instances. Training on their data set is really time consuming, but in our case, you can easily try out different ideas with this data set. The lessons for instruction tuning we learned from this work include that the task or the instruction diversity is very important, and we need a larger model. Larger actually means more powerful base model to do this instruction following. And finally, like I want to emphasize, like you don't need the large number of training instances if your goal is to generalize to new task. Overfitting is a big problem here. There are some later follow-up work on tackling this overfitting issue. I will not cover here, but I think it is a very important topic. Okay, so with the SuperNI instruction dataset and the TK instruction model we built, then we ask this question: can we try these models for creative tasks? Like we want this model to be similar as InstructGPT or like ChatGPT or GPT-4. We set out demo, but sorry, these models can be very disappointed. So if you try some generative tasks with these models, Um, one example is this: write a sentence with the following words, and the words we provide is Apple cash tag. It's actually very simple, right? Like you might expect some output like Apple is a big tech company that has a lot of cash, something like that. Composing a sentence from words shouldn't be that hard. However, this model is not doing very good on this task. In this example, it basically repeats the input. If you change the format of these instructions, it can do better. Like basic here, the model outputs a sentence, Apple Cash is the new tab, but it's still not that good. It's not a meaningful sentence. We actually tried all the other models trained on existing LP datasets, including T0 from Hugging Face and the Flantify from Google. All these models cannot do this task. You can see T0 outputs cash in the bank, a tech company. Flantify outputs cash for tech and cash for people. These are not sentences. So what I'm missing there? So we tried Yizhong. Actually, this is the first version of Yizhong, text 70001. It's great. It outputs Apple is a tech company that deals in cash, although it's not factually correct. I think it also deals in other formats. So what is the most important factor? Let's take a look at the training of Yizhong. So in OpenAI's paper, Yizhong paper, they they told us this process of building Yizhong from GPT-3. Basically, they get in the first stage, they get a lot of contractors to write prompts and demonstrations for training an instruction following model. In this stage, they collected around 11K instructions of, like they call it, prompts. And after this fine-tuning, supervised fine-tuning with this initial data, they start deploying these models. And so their API users provide their customer prompts. Then they employ another batch of contractors to label the desired outputs for these customer prompts. Then they do another round of supervised fine-tuning. In the final round, they actually got more customer prompts. And now they ask the human labelers to provide a preference over models generation. And with this preference data, they train a preference model that can be used to do the reinforcement learning with human feedback. All these three stages lead GPT-3 to Yizhong. So as we can see here, there are a lot of creative queries from users, and there are a huge amount of human labeling. But the problem is we cannot see this data. We cannot use this data because OpenAI is not that open. So it's natural that we want to construct a similar data set. But as researchers, we don't have real users, right? The first idea we thought was, okay, can we do some crowdsourcing with amateur? We have money, we have the funding to do this kind of study. We did a pilot study within our group. We set up a demo. We did a pilot study for annotating new tasks, but we found that writing, for the first point is writing these diverse tasks or instructions really requires creativity. Imagine I ask you to write tasks. You might have some tasks coming to your mind, but after you write down 10 or 20 tasks, you start running out your creativity. It's very likely. I annotate a lot of these instructions. Actually, I spent probably 2 days annotating 50 meaningful tasks. This is a lot of work, and it really requires creativity. The second problem is when after you get the instructions, writing the instances for different instructions can also be very hard because it requires broad expertise. Like if I have an instruction like writing a Python program for quicksort, how long you need to write this program? If the instruction is writing an essay about environment protection, how long do you need to write an essay? Probably 30 minutes or at least 50 minutes if you can use Google or some other search engine and copy paste from the internet. But this is basically to say all these this crowdsourcing can be very hard and impractical for crowd workers because all their expertise required. Then we discard that idea and we ask another question. Can we use these models to generate instruction data? Because if you still remember this big circle from pre-training, this model should have a lot of knowledge. It should have seen a lot of the tasks on the internet. If we have a way to probe this out, the model might be able to generate a lot of diverse instructions and data. So we really tried this idea. We first found that, okay, we can prompt GPT-3 to generate the instructions. This is with the DaVinci engine. So it's the vanilla pre-trained GPT-3. But still, you can see here, I asked the model to come up with a serious task. I put several C tasks here as the to prompt the model to generate similar data. The model generates meaningful tasks. Let's zoom in. So the task generated includes create a list of 10 words that has the letter K in them, or create a list of all countries and their capitals from Africa. And the third one is helping a person to look for a job. This is hard. But the last one is write a program that does something. All these tasks generated are meaningful. This is quite promising. And then after generating these instructions, we want to generate instances for each instruction. Can the model do this? Answer is yes. If you prompt it in a proper way. So the prompt that we gave it is like come up with an example for each of the following tasks, and we describe, okay, each example should have one output field and one output, and the if it requires the input, then you should generate that. We have a bunch of demonstration examples for diverse tasks, and then for the eighth task, we have our new instruction generated by the model, and the model can generate both the input sentence and the output. You can see this is like correct output. This is actually very simple, right? Like basically it's a prompt. It's prompting for GPT-3 models. This simple idea works. With these findings, we build a pipeline for generating data. The pipeline contains several stages. At first, we like ourselves wrote 175 C tasks that can be used to prompt the model, as I have shown before. And then in the first step, we generate the instruction. One instruction example, it generates, give me a quote from a famous person on this topic. And then we classify whether this instruction is represent a classification task or a generation task. For classification task, we did output first instance generation. The reason is that for classification task, their output space is limited. actually it's easier to first generate all the possible labels and then condition the input on the labels. This makes the input more balanced and more relevant to the class label. For the generation tasks, because the output space is infinite, we cannot generate the output directly. So we generate the input first, and we still found the model can generate the meaningful input and output. After this generation, we did some simple filtering. We discard all the evaluate, based on some rules, we discard the evaluate tasks and add all the meaningful tasks to the task pool. And then we can keep this loop. Every step we sample task from this task pool and then basically grow this data set larger and larger. Totally, we generated 52K instructions with this GP3 model, the deficiency engine. And because we did very strict filtering, we didn't allow instruction that has rouge L overlap larger than 0.7. So this actually benefit us in generating very diverse instruction. Basically, there is no exactly the same, like no very similar instructions in our dataset. Let's take a look at some examples here. The task generated include, the first example is an information lookup. It's like given an address and the city come up with a zip code. And this is like a real address. It's a real address in San Francisco, and the zip code came up here is valid. The second example is to fill in a form, application form for a job. Actually, this form is much longer, but so yeah, I have to cut it off to fit in the page. But it's actually a very good example that shows the model can generate a very creative input format. And the third example is to write code. We didn't generate a lot of coding tasks, but generally, like this model, if you prompt it to do this, it also knows such tasks. And the last two are like more generative. Like the first one is to give some suggestion on finding apartment. The last example is to write a letter from the perspective of a cat. It's meaningful, but it's like very imaginary. We reviewed the data generated by the model. We saw around the 40%, like in terms of all the fields, both the instruction, the input, and the output. On average, we have 54% of the generated data valid. This actually tells us that there are a lot of noises in the data, but still we can use this data. We come to the concept of self-instruct. Basically, we fine-tune the original model, GP3, with the data generated by itself. I don't want to cover the details, but let's look at the performance. The first set of evaluations were done on SuperNI instruction. We basically compare the self-instruct version of GP3 versus the original GP3. We saw big improvement here, like 33% jump. This is because the original GP3 cannot follow any instructions. So its performance is really poor. And then the second comparison is the self-instructed GP3 versus the instruct GPT. We see, okay, we are very close. Only like the gap is within 1 point. And the third point I want to mention is we compare the because we have the SuperNI instruction, we have the training data. We compared the GPT-3 model trained on SuperNI instruction versus the GPT-3 model trained on both self-instruct and SuperNI instruction. We found that the self-instruct data bring in complementary improvement to these existing data sets. So this actually confirms the finding in SuperNI instruction that more diverse data, more diverse tasks can be helpful for the model. And then we did another set of evaluation. This is because in SuperNatural instruction, most of the tasks are still classification tasks. So we annotated 252 user-oriented instructions that are focused on more creative and generative tasks. And then we did expert evaluation by ourselves. We did a 4-level rating. The best rating we have is the output is correct and satisfying. And then the second level is it is acceptable but with minor errors. The third level is with significant errors. The fourth level is like the generation is totally irrelevant. We first compare self-instruct version of GPT-3 versus the vanilla GPT-3 or GPT-3 trained on existing instruction data sets. We can see that on this creative, generative instruction benchmark, self-instruct can outperform all these existing models, and actually it's a big improvement. Then we compare this self-instruct model with OpenAI's different version of Yizhong GPT. Unfortunately, we still have a gap from their models, but we can see that self-instruct is very close to the performance of their 001 model, their first version.
Yeah, so when you were doing the dataset curation, did you look into any kind of like results that would be out there elsewhere that you could get from maybe some scraping? Like, I'm just thinking that there are probably a lot of creative tasks and annotations on platforms like Reddit, where I know there are like creative writing subreddits that could potentially give you really good data that wasn't actually like self-generated.
Right. We didn't do that, but yeah, this is possible. But the problem is in like Reddit data, the formats are still very limited. Like creative writing, it's still like you have the some needs there, and like I would say it's not like there are not tasks like writing code or like fill in the form. It's not like that diverse. Yeah, but like there are a lot of tasks on the internet. Yeah, we can like basically the idea of self-instruct is also based on there are a lot of tasks on the internet. Okay, so we did some additional analysis. One is the data sets. Again, like we tried train the model with different size of the generated data, and we see consistent improvement by including more data here. And again, the axis is log scale, so the gain starts slowing down after the size of 16K. Another analysis is the data quality. We basically try to improving the output quality by using a better version of the GPT model. You can see here in terms of the final performance, we see a very big jump, like 10% jump. This is to say, if you have some resource that can improve the quality of this generated data, you can see much better performance. The takeaways here are like, we are probably the first one to show that if you want to do these generative tasks or creative tasks, you actually don't need a huge amount of label data to get a reasonable performance. The language models themselves know a lot of the tasks or skills from pre-training. One aspect of this instruction tuning is to kind of elicit these skills. And in this paper, in this work, the self-instruct work is an extreme setup that only elicits skills from the model itself. We are not injecting like new skills other than the very small number of C tasks. And the self-instructed is actually applicable to a broad range of language models. I will show some results later. More broadly, I think the future, like we saw this challenge of building data sets from using human from scratch. And we solved this issue by using large language models or AI models. So in the future, I think when we think of building data sets or think of new tasks, we should always use human AI collaboration for this data creation. Finally, I want to discuss some recent trends. We know that, like, you probably know that there are like a lot of recent work on replicating ChatGPT, Yizhong or ChatGPT. These are basically different variants of self-instruct. The Stanford Alpaca is probably the most famous one. And there are other ones from UCB, UCSD, and MSR. I really like this image from MSR. I think it's like it's generated by Stable Diffusion. Like basically, it's to say, okay, we have these llama models, and you can teach it with a very strong AI model from OpenAI. And what are the? I want to summarize the differences or the improvements of these models. So basically, in the self-instruct paper, we kind of teach the model itself by itself. In these recent works, they are kind of distilling the knowledge of the tasks from more powerful OpenAI models into a smaller llama models. And they changed our pipeline a little bit. They didn't consider classification tasks because I think no one cares about classification right now. So they just generate a lot of creative tasks. And some of them use better C tasks. Vicuna and Baize Koala, they use the data from shared GPT forum. This forum contains a lot of GPT, a lot of prompts and GPT outputs coming from the users. One work by the incorporates the dialogue format. I think Vicuna also has the dialogue format. All these models are based on recent llama models from Meta. There are some concerns here, like the OpenAI's terms of use says you cannot use the output of from this service to develop models that compete with OpenAI. This is a very vague restriction. We are not sure what it means by compete, if we do research, are we compete with OpenAI? We are not sure. But still, it's okay. We have some solutions. One solution is we just use the original self-instruct, but we change the OpenAI models with llama. Here are some samples I generated with llama model, and you can see it has like these are valid tasks, valid instructions and output. And then another solution is to spend a lot of money and effort on the human labeling. I think there will be several open source human labeled instruction datasets coming out very soon. Actually, there is one example from Databricks, this free Dolly dataset. They have 5,000 employees, and they ask these 5,000 employees to write instruction data for themselves, and they open source this dataset. It's actually pretty good. Finally, I want to provide some promising direction that I think will be very interesting to explore. The first one is actually related to this instruction tuning. We want to understand what happened in this instruction tuning stage. There hasn't been a lot of work on this. And I think it's very important. And the phenomena of overfitting is also very interesting to explore. Like we might need to redefine overfitting in this. There are a lot of people actually working on the second point, combining these efforts and building an open source general purpose model that are similar to ChatGPT or GPT-4. We will have a lot of data coming out, and we will have more base models. Llama is a good example, but I think we will have several new ones in the near future. I mean, this year. And the open source community actually are quickly catching up. The third one is we might need to develop, like, let's assume we have ChatGPT and we have like an open source ChatGPT. We want to further improve it. We probably need better algorithms here to get further improvement, because improvement is very challenging for these already very powerful models. Some of the promising formats I saw included the human feedback, different forms of human feedback, and probably we can also use the concept of self-improve. I'm not sure how to do that, but there are some recent papers on this topic. I'm personally very interested in the specialization and personalization of these models. I think everyone will own their own ChatGPT, and we need to develop algorithms and platforms to personalize these models for different needs. Finally, I want to emphasize that if you still remember these two circles, the size of the pre-training is actually I think it won't grow very much in the future, because we are kind of running out of the pre-training data on the internet. But the data for fine-tuning stage starts getting bigger and bigger because a lot of users are using these models. You will see extensive data in the near future. This is why this instruction tuning stage, or like fine-tuning stage, will become more promising and more useful in the future. That's it.